This video is going to look at covalent bonding based on these outcomes from the SQA National 5 Chemistry course. We're going to look at what type of elements form covalent bonds, what a covalent bond is, how you can draw diagrams to show how outer electrons are shared to form covalent bonds in a molecule. We'll look at diatomic molecules, and we'll also look at molecules that contain double and triple covalent bonds. So this is the first learning outcome here. Covalent bonds form between non-metal atoms. I would say usually there are one or two exceptions, but you can assume that if you have a chemical bond between two non-metals, such as these ones, hydrogen, oxygen, carbon, nitrogen, fluorine, chlorine, phosphorus, and sulfur, etc., you can assume that bonds between them will be covalent. To determine whether an element is a metal or a non-metal, you will have access to your data book. And you can see this is page 4 of the data book, and there's a key here. You can see there's a dark line on the periodic table, and below this dark line are elements which are metals. Above this dark line are elements which are non-metals, which I've highlighted in red here. Another page in the data book that may be more useful for doing covalent bonding problems would be page 6 in your data book as shown here. So you can see not only does it have a key here, which will allow you to tell if an element is a non-metal or a metal, it has the electron arrangements for each element. And this is useful if you're doing electron sharing diagrams when you need to know the number of outer electrons present in each element. To demonstrate how a covalent bond is formed, I'm going to use hydrogen as an example and these ring magnets. This large ring magnet is going to represent a positive nucleus containing one proton, and this small ring magnet is going to represent a negative electron. This wouldn't be regarded as a stable arrangement, unlike helium, because we've not filled that first energy level with 2 electrons. But this is what hydrogen does to try and achieve the stability that helium has. When the hydrogen atoms come together, you can see we've got these negatively charged electrons. Initially, we might see they might repel each other, like this. But if they come close enough together, what happens is the electrons come together and form a pair between the 2 atoms. I don't know if you can see that. So we have a shared pair of electrons between the 2 atoms, and that's good from a stability point of view, because now this hydrogen atom's got 2 electrons at its energy level, and this one has 2 electrons too. And you can see that these paired electrons cause the atoms to join together and form a chemical bond. And we call this bond, in which we have a shared pair of electrons between 2 non-metal atoms, a covalent bond. So our definition of a covalent bond is that a covalent bond forms when 2 positive nuclei are held together by their common attraction for that shared pair of electrons. So we're going to look at how fluorine forms a covalent bond between its atoms. Fluorine has got 7 outer electrons. It needs 1 more to fill that energy level. And what fluorine atoms do is they come together, and these 2 outer electrons are going to come together and be equally shared between the 2 fluorine atoms to form a covalent bond. And this allows each fluorine atom to have 8 outer electrons between it. So you can see the covalent bond here. This is the shared pair of electrons. This time we're going to form a compound with covalent bonds. So we are going to join hydrogen to fluorine. Hydrogen has 1 outer electron. Fluorine has got 7 outer electrons. So they both need 1 more electron to fill their energy levels. And what they do is they come together and share a pair of electrons like this. So now the hydrogen has got 2 outer electrons, making that a stable arrangement, and the fluorine now has 8 electrons in its outer energy level. So this covalent bond allows each atom to have a stable electron arrangement. So we're going to look at how diagrams can be drawn to show how outer electrons are shared to form covalent bonds in various molecules of the elements of the periodic table. So we're going to start off with hydrogen atoms. Hydrogen atoms have 1 electron. I've shown this with an X. To fill that first energy level, they need 1 more electron. So what the hydrogen atoms do is they share their electrons like this to form a covalent bond, and you'll see that each hydrogen atom now has 2 electrons present in that first energy level. And we now have a hydrogen molecule with a covalent bond between the 2 atoms. You could show it like this if you used a molecular model. What about if we used fluorine? Well, fluorine has 7 outer electrons. Remember, fluorine has the electron arrangement 2-7. We are going to ignore the inner 2 electrons and just focus on the outer 7. Fluorine needs 1 more electron to fill that energy level. So what it will do is it will share an electron with another fluorine atom to form a fluorine molecule with a covalent bond containing a pair of shared electrons between the atoms. So a fluorine molecule will be linear like this. You would have 2 fluorine atoms joined together with a covalent bond. Okay, let's look at oxygen. Oxygen has 6 outer electrons. It will need 2 more to fill the energy level. So what oxygen does is it forms a double bond between them, consisting of 2 shared pairs of electrons. And you can see if I look at this atom on the right hand side, we've got 2, 4, 6, 8 electrons now in the outer energy level of that oxygen, and likewise with the left. So we now got an O2 molecule with a double covalent bond in it like this. This is what the molecular model would look like. Finally, we're going to look at nitrogen. Nitrogen has 5 outer electrons. It needs 3 more to fill that energy level up to 8 for stability. So what will happen is another nitrogen atom will approach, and it will share 3 electrons with the other nitrogen atom to form a triple covalent bond consisting of 3 shared pairs of electrons. So we have a triple covalent bond between the nitrogen atoms. So our nitrogen molecule contains 3 covalent bonds like this. So we've got a triple bond, and this triple bond makes nitrogen very unreactive. The molecules we've just looked at, hydrogen, fluorine, oxygen and nitrogen, consists of 2 atoms joined together by covalent bonds. There are 3 other elements that can do this. There's chlorine, bromine and iodine, 3 other halogens, and there is a name we give to these molecules. We call these diatomic molecules. The di meaning that there's 2 atoms present in the molecule. Electron sharing diagrams can also be used to show how compounds are formed. So in this first example, we're going to join hydrogen to fluorine. You'll notice that the fluorine has got 7 outer electrons, therefore we need 1 more electron to fill that energy level. And it can do this by sharing an electron with a hydrogen atom, like so. So now the fluorine has got 8 outer electrons in its outer energy level, and that hydrogen atom now has 2 electrons in its first energy level, filling it and achieving stability. So we have hydrogen fluoride being formed, a hydrogen fluoride molecule. Now what happens if we joined hydrogen to oxygen? Oxygen has 6 outer electrons, so we need to attach 2 hydrogen atoms to that to fill up oxygen's outer energy level to give it 8 electrons. And likewise the hydrogens have 2 in their first energy level too. You'll notice we have H2O now being formed. We have a water molecule being formed. Let's try this with nitrogen now. So nitrogen has got 5 outer electrons, so we need to stick on 3 hydrogens to get the number of outer electrons in nitrogen up to 8. So now we've got 1 nitrogen joined to 3 hydrogens, so we have a NH3 formula here. We formed something called ammonia. Finally, if we take carbon, which has got 4 outer electrons, like so, you'll see it needs 4 more to fill the energy level, so we need to stick on 4 hydrogen atoms to get carbon's outer energy level full with 8 electrons. Get the last one on. So you can see that now we've got 1 carbon and 4 hydrogens, So we have methane CH4. Okay, so we're going to try an exam question now in which we're asked to draw a diagram showing all outer electrons that will represent a molecule of chlorine Cl2. To find out the number of outer electrons present, that's our starting point, we're going to need to look in our data booklet and turn to page 6, where we can find out the electron arrangements of the elements of the periodic table. So if you turn to page 6 of your data book and look under the halogens, you will find chlorine present with an electron arrangement of 287. So we know the electron arrangement of chlorine is 287 from the data book. We're only interested in the outer electrons as these are shared during covalent bonding, so we can ignore those inner two energy levels containing 2 and 8 electrons, and we can focus on these 7 outer electrons. The next stage is to draw an electron diagram for chlorine. So it's a good idea to draw the symbol and put a circle around it, and then put in the 7 electrons. Now it's not a good idea to draw the electrons randomly around the circle. It's much better to have some kind of organized system to do this. So one good system is to think of this as a kind of clock and draw the first 4 electrons on it at positions 12 o'clock, 3 o'clock, 6 o'clock and 9 o'clock, all far away from each other, and then you pair them up as you get the 5th, 6th and 7th and so on. So if you're going to draw chlorine, a good idea is to draw the first 4 at these positions and then start pairing them up. So you can see we've got 3 pairs of electrons and an unpaired electron at this side. This atom will need 1 more electron to fill its energy level. So what we can do is put another chlorine atom beside it and put in this atom's 7 electrons shown as crosses like this. So there's your 4 there. There's the other ones, and you can see within the 2 atoms we've got a shared pair of electrons. This shared pair of electrons allows this chlorine atom to fill its energy level with 8 electrons, and this chlorine atom likewise has 8 too. Now, you don't have to have circles on one and X's in another. Circles on both atoms is fine. You don't even have to have the circles, the big circles either. As long as you show a shared pair of electrons between the 2 chlorine atoms, that's acceptable. And you can get away without using the symbols here because we've only got chlorine in here. So these are all acceptable. What wouldn't be acceptable is not showing the electrons being shared between the 2 atoms. So here's an example. We don't have a pair of electrons shared between these 2 atoms here. You can see that this one has got 1, 2, 3, 4, 5, 6, 7 electrons in its outer energy level, so that would be incorrect. So make sure you've got the electrons in this overlap region, or at least on the lines, not outside like this one. So that would be incorrect. This exam question is asking us to do the electron sharing diagram for a compound this time, in this case hydrogen sulfide, H2S. We're going to need to go to the data book, page 6, to look at the electron arrangements for hydrogen and sulfur to look and see how many outer electrons are present for each of the elements in that compound. Once we have the number of outer electrons, it's a good idea to start with the element that has the most outer electrons. In this case sulfur, which has got 6, compared to hydrogen, which has got 1. So we get the chemical symbol for sulfur down, draw a circle around it, and put our 6 electrons in its outer energy level as shown. You'll see we've got 2 unpaired electrons here. We also have 6 outer electrons, so we need 2 more to fill the energy level, and we can get those by sharing electrons with 2 hydrogen atoms as shown here. So now you can see that sulfur now has filled the energy level with 8 electrons, while hydrogen has filled that first energy level with 2 electrons. So we now have a stable arrangement and a molecule of hydrogen sulfide being formed. Things to note for marking schemes: it doesn't matter if you've got all circles or all crosses. It doesn't matter if you don't have big circles like this showing the energy levels. It's okay to have something like this, as long as you show the shared pair of electrons between the sulfur and the hydrogen each side. It's also a good idea to show the symbols as well, so you know the origin of the electrons present in each molecule. So these are good. What's not good is if you don't show the clear diagram with the sharing of electrons between the atoms. So you can see in this one, this hydrogen has only one electron in that first energy level. This electron needs to be moved over here. So you really need to have the electrons within this overlapping region or on the lines to get the mark. So this would not get the mark. Here are two compounds I wanted to try drawing electron sharing diagrams for. The first is ammonia, the second is methane. So have a data book, a pen and paper handy, and have a go. Pause the video and have a try. Okay, so let's look at ammonia first. If you look in the data book, nitrogen has got 5 outer electrons, so we can draw those. We have 3 unpaired electrons, i.e. 3 more electrons to fill this outer energy level, so we need to add 3 hydrogen atoms, which can each contribute 1 electron to be shared. So now we have a full energy level for nitrogen with 8, and full energy levels for each of those hydrogen atoms with 2 in the first energy level. For methane, carbon's got more electrons, it's got 4 electrons. If you look in the data book, it has an electron arrangement 2-4. We need 4 more electrons to fill that energy level, and we can get those by adding 4 hydrogen atoms with their single electrons to make a full energy level for carbon with 8 electrons. And again, these hydrogen atoms have all filled their first energy level with 2 electrons. I think this is an interesting exam question because I think it's the most difficult one that I've seen come up, and that we have to represent a molecule of nitrogen gas N2 showing all outer electrons. So we'd get a symbol for nitrogen, we'd have a circle, and we'd draw our 5 outer electrons on that. Now, up to now I've said it's a good idea to draw the first 4 far apart. If you think of this as some kind of clock, draw the first 4 positions 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock before pairing up the 5th one, like this. And you could do the same with another nitrogen atom representing the electrons as crosses. The difficult part is pairing up these 3 unpaired electrons to fill that up to 8. And it's difficult because they're kind of well spread out. You can't just stick 3 nitrogens on here like you can with hydrogen. So you have to adjust the rules slightly for this to occur. So this nitrogen atom has got 3 unpaired electrons. If we're going to share these electrons with just one other atom, then it's a good idea to shift these electrons to one side to allow that to happen. So you can generally assume that if you have a diatomic molecule that has a double or a triple bond, in this case we've got a triple bond because this molecule is going to have 3 shared pairs of electrons. And it's a good idea to have the other pair of electrons that are not shared at a different side of the atom as well. So you'll soon see what happens when I show this diagram. If we move this electron over here, and we have 3 unpaired electrons at the right hand side, it allows these 3 unpaired electrons to be shared with the other nitrogen atom. So if we have another nitrogen atom and we add our 5 electrons, the first 3 we can pair up with the ones from the other nitrogen atom, leaving 2 at the other side. Then we've got this triple bond being formed with 3 pairs of electrons. And also we have the stability associated with having 1, 2, 3, 4, 5, 6, 7, 8 electrons present on the outer energy level of each nitrogen atom. Now it doesn't have to be X's and circles. It can be all X's or all circles, that's okay. When you're sharing them, it's a good idea to keep the electrons within this overlap area or at least on the line. So there's another example of an electron sharing diagram that's acceptable. If you're confident enough, you can do without the circles and just make sure you show that there's 3 shared pairs of electrons between the 2 nitrogen atoms. Here's one last example for you to try then. So I want you to draw a diagram showing all outer electrons that will represent a molecule of oxygen gas O2. So pause it and have a go. Looking at the data book, we know that oxygen has an electron arrangement of 2-6. So we can draw an oxygen atom with 6 outer electrons. Notice that I've put 2 unpaired electrons at the right hand side, which we can use to share with the electrons from another oxygen atom. So here's the other oxygen atom. We're going to put its 6 electrons as X's in its outer energy level, and we've paired 2 of them up to form a double covalent bond. So that's our completed electron sharing diagram for an oxygen molecule, in which we've got 8 outer electrons here and 8 outer electrons here, with 2 shared pairs of electrons in this area in the middle. So look at lots of worked examples of these and keep doing lots of practice, and you'll get really good at doing these. I hope this helps.